In this video, we're going to do an example problem where we look at the force from a carrying current wire on a moving charge. And this will be a magnetic force example where we both are trying to find the magnetic field based on the object that creates it and find the force on the object that then is feeling the force. Now, the particular description is that an electron is moving directly away from a current carrying wire at 10,000 meters per second. The current is carrying a 3 amp, the wire is carrying a 3 amp current, which is a pretty large current, and the electron is currently 10 centimeters away. I want to find the force on the electron, which will include both the magnitude and the direction, and the acceleration of the electron, which will also have the magnitude and the direction. The first thing I'm going to do is find the direction of the force on the moving charge. So to do that, I would want to use one of the right-hand rules, the first right-hand rule. And I'll pop up a video of me so that you can see me work through this. Okay, so here I am. If I wanted to know the direction of the force on that moving charge, the first thing I would have to do, I'd have to know the speed and the velocity the direction is moving. But I'd also have to have the magnetic field, because if I use this right-hand rule, this is the speed, this is the magnetic field that it's responding to, and this is the force that it's being pushed on. So I have to know both of these before I can find that, to know how to orient my hand. So we'll have to just take a step back and say, I need to know the magnetic field it's responding to. When you do that, you have to ask, what is pushing on it? What object is actually causing it to feel a force? In this case, it's the wire. It's the current in the wire. So we have to step back and say, okay, well, what is the magnetic field of that current carrying wire? Because that's what it is doing that is creating the force. And to find that, we have to use our second right-hand rule, which tells us about the magnetic field created by a long current carrying wire, so a long straight wire. And remember, when we do that, I'll use the vector one, because all I want to know is the magnetic field at the location of the moving charge. Reason being is that's the magnetic field that the electron is responding to. It doesn't know about the magnetic fields at every other location. It doesn't care about them. It only cares about the magnetic field where it is. So, to do that, I'm going to have the current carrying wire. This will be my finger. I will put my thumb in the direction of it. Then I will stick my hand directly out to the right towards where that point charge is. And if my hand is now fully extended in the correct direction, I can bend my fingers 90 degrees. And again, it's hard to show in the video because of the way that the camera is oriented, but that is directly into the slide. So it's directly into the page is the way I'll phrase it. So that means the magnetic field is into the page. I'll draw a quick arrow right here to indicate that. So now I've put on the magnetic field of the wire, shown the direction of it. Now I have to take the second step where I use the first right-hand rule, this one, in order to find the direction of the force. Okay, so how do we do this? Well, first off, we should note that we're looking at the force on an electron, and an electron is a negatively charged object. I'll use the positive charge, use my right hand, and negative charge is my left hand. So I'll use my left hand in this case. Be careful, you're very conscious about which hand you're using. Okay, so I need to point my thumb in the direction that the charge is moving, which is off to the right. I need to move my index finger in the direction of the magnetic field, which is into the page. Then my index finger, or middle finger, excuse me, will point in the direction of the force on this negative charge. So it's going to be pushing it down, directly downward. Now the other thing, while I still have my hand in this direction, I want to note is I'm going to find the magnitude soon, and I want to find the angle between the magnetic field that it's responding to and the direction that it's moving, which is the direction between my thumb and my index finger. In this case, where the velocity is directly to the right and the magnetic field is directly into the page, that angle is 90 degrees. So I'll draw the force and note that the theta in my formula I'm going to have in a second is going to be 90 degrees. I'll switch to red for the force so that it's clear that the different types of quantities have different colors associated with them. So this is the force of the wire on the charge, or the electron. So it's a downward force in this case. Now, I'll also note, as I mentioned, that theta equals 90 degrees. Well, what theta are we talking about? That is the theta that is in the force equation. So now I know the direction of the force, which I'll do first. I'll find the force. I need to know the magnitude. The magnitude, again, everything is implicitly going to be in absolute value signs. Here, maybe I'll explicitly show it. Has the charge, the velocity, the magnetic field, and sine of that angle. I'm going to simplify this a little bit, given a few things I already know. Since sine is 90, the angle is 90 degrees, sine of 90 degrees is 1. So this part simply is reduced down to 1. The other thing is that the charge of the electron is negative E, and I'm going to use the absolute value signs to say that it's just E, using the positive. And what I have is that this is now EVB, where again E is the charge of a proton, that 1.6 times 10 to the negative 19th coulombs, which is the same amount as the charge of an electron. Now, if I want to find this, I'll just add some subscripts to be a little bit clearer. I want this to be the wire on the electron. So this is the charge of the electron, and this is the magnetic field of the wire. So how to find the magnetic field of the wire? Well, luckily we have a formula for this. The magnetic field of a long straight wire is simply mu naught times the current in that wire divided by 2 pi times the distance from the wire. So I'll plug that in here. So now I find that the force of the wire, which I'm just going to write as W, on the electron is EV mu naught I over 2 pi r, which if I plug in the values are as 1.6 times 10 to the negative 19th coulombs times 10,000 meters per second times 4 pi times 10 to the negative 7th volts seconds over amps meters. Continue in the numerator with a 3 amps is my current. And now in the denominator, I'm going to divide all of this by 2 pi times the distance away from the wire, which in this case is 10 centimeters, or in meters, 0.1 meters. And when I multiply this all out, I get 9.6 times 10 to the negative 21 newtons, which is an extremely small force. So this is the magnitude of the force, and then the direction of the force is downward.